All right, let's solve the complete eigenproblem for this matrix A. So what does that mean? It means find the characteristic polynomial, use that characteristic polynomial to find the roots, which are the same as the eigenvalues. And then once you have the eigenvalues, then you want to find the corresponding eigenspaces. So that's going to be the subspace consisting of all the eigenvectors. And then once you've got all of the eigenspaces worked out, then you want to check the dimension of each one of those eigenspaces and see if they add up to, in this case, 3. So if they add up to 3, then the thing is diagonalizable. If they don't add up to 3, then the thing is not diagonalizable. And if they do add up to 3, if it is diagonalizable, then we need to find a matrix P that will conjugate this thing into a diagonal matrix. And then we just want to do the multiplication and get the actual diagonal matrix in the end. So, step number 1, find the characteristic polynomial. We've seen this a bunch of times. It's a determinant. So you subtract x off of the main diagonal and then take the determinant. So here that matrix is. And so we can use cofactor expansion along the third row or third column. They're all 0, so it doesn't matter. So I get negative 2 plus x, and then times, well, probably positive. Either way, it doesn't matter. And then times the determinant of this thing. So 1 minus x quantity squared minus 9. So then you can work all that out, right? You FOIL this stuff inside. Don't FOIL this thing. It's already factored. It's already a linear factor, so leave it alone. FOIL this thing and then factor it. So in here, you're going to get x plus 2 times x minus 4. So when you collect everything, you get x plus 2 squared times x minus 4. And so this thing tells us that the eigenvalues, so that's part 1 done. We found the characteristic polynomial, and we found it in factored form. This is how you want to write those characteristic polynomials down. Don't leave it like this, write it like this. So from here you can see exactly what the eigenvalues are. They're the roots of this thing. So lambda equals negative 2 and lambda equals 4 are the 2 eigenvalues. And while we're at it, what's the algebraic multiplicity of negative 2? Well, it's the power, right? 2, right? So the algebraic multiplicity of negative 2 is 2. And the algebraic multiplicity of 4 is equal to 1. So to compute the eigenspaces, we're going to subtract each eigenvalue off the main diagonal and then compute the null space, right? That's always how you find the eigenspace. So I'm going to subtract negative 2 off the main diagonal, which means I'm going to add 2 to everything on the main diagonal. So I get a 3, and then 0. So 3, 3, and 0. And so to find the null space, well, you can divide by 3, right? Put the thing in reduced row echelon form, and here you get 1, 1, 0 across the top and zeros everywhere else. So we've got 2 free columns. That means we should have a 2-dimensional null space. And so how's that going to work? It goes x plus s is equal to 0. So x is equal to negative s, y is equal to s, and z is equal to t. So as per usual, split it up along s and t, and you get these 2 spanning vectors, negative 1, 1, 0, and 0, 0, 1. So that means the dimension of the eigenspace associated to negative 2 is equal to 2. And then for the eigenspace 4, we're going to subtract 4 off the main diagonal. So we get negative 3, negative 3, negative 6. We want the null space of this matrix. So put the thing in reduced row echelon form, and you see that the null space is just spanned by this single thing. So now we can see if the matrix is diagonalizable or not. So I would call this part 3, and then part 3 is find the eigenspaces. And now for part 4, you can see that the dimension of the eigenspace associated to negative 2 plus the dimension of the eigenspace associated to 4, what is that? It's going to be 2 plus 1, so 2 plus 1, that's equal to 3. That's equal to the size of the matrix. And so that's a yes to diagonalizability, right? The sum of the dimensions of the eigenspaces is equal to 3. Of course, another way to see that is the geometric multiplicity of -2. That's equal to 2. And remember, when we wrote down the characteristic polynomial, we got x plus 2 squared, so that's the same as the algebraic multiplicity. And the geometric multiplicity of the eigenvalue 4 is 1. That also matched the algebraic multiplicity of that of the 4 factor, right? The x minus 4 factor. So this is, to me, this is the easiest way to check for diagonalizability. So you can also check, as we just mentioned, the algebraic geometric multiplicity business, or you can check that these 3, right, so 3 that matches the size, these 3 vectors are linearly independent eigenvectors. So you've got a basis of eigenvectors, and so that's another way to say yes to the diagonalizability question. So now that we've written it all out, now I can see that this eigenproblem has 6 parts that we should identify. So part 1, characteristic polynomial. Part 2, find the eigenvalues using the characteristic polynomial. Part 3 is to find the corresponding eigenspaces. Part 4 is to use those eigenspaces, the dimension of the eigenspaces, to say yes or no to the diagonalizability question. So if you say no, then you can stop there at step 4. If you say yes, then you need to continue on to steps 5 and 6. So step 5 here is to find a matrix P that will conjugate A into a diagonal matrix. So you just arrange these things, right, these linearly independent eigenvectors, into a square matrix. And because these are all linearly independent, we know this matrix will be invertible. So that's step 5, find the matrix P. All you have to do is arrange the eigenvectors as columns of a square matrix. And then the last step is to compute P inverse and then find this product. And the order does matter. If you try to do P times A times P inverse, you probably won't get a diagonal matrix. It's really important that if you take P to be the matrix whose columns consist of the eigenvectors, then the product that you want is P inverse times A times P, and that will give you the final diagonal matrix. And again, notice, the only thing that shows up on the diagonal are the 2 eigenvalues in this case. This thing shows up twice because its eigenspace has dimension 2. This thing shows up once because its eigenspace has dimension 1. So these 6 steps complete the full eigenproblem for this matrix A.